in some sense, we will start fresh. So, this lecture is some basic language. So the one basic concept that I will underline here is the concept of a sheaf. And of course, many of you know concepts such as vector bundles, etc. So this is going back to the basics of the subject. So let's start with an example. Now that you're here, I can show you. So an example that you all know, X should be, in this example, a complex manifold. And if you have an open subset in X, then the notation is OX. This will be my notation. Maybe I've used it already, actually. These are just the functions f, which are holomorphic on U. And we consider this to be a mapping. There's fancy language here, but which I avoid, I don't like. So, but this is a mapping from U to OX of U. Associates to an open set. Yes.
So F is a function to P1 or to C?
Yes, thank you. Holomorphic function. So not a mapping, so a holomorphic function. Thank you very much. I mean, because we talked about mappings. So I mean holomorphic to C. Okay? And you think of this as a mapping from open set. In X to, well, you see this has a lot of structure here. This is a C algebra, so quite often we only require two groups. We only need one operation here. Here there are many operations, multiplication and addition. And in fact, it's an abelian group, and it's an algebra and so on. So to some algebraic structure. Usually just a group is required. And it's should be compatible with the operations on sets and the operations here. So, as you know, there is an operation on sets. If U is contained in V, that is sort of a, no, I want to make it the other way around. U contains V. Something like this. U is greater than V, say. Some sense I've always said about this. This is the injection, the operation, the injection of U to V. Right? Then this operation here should correspond to the restriction mapping, which I always write like this, from OX U to OX V. So injection here corresponds to this is a functor. This is a so-called functor, but I don't care about this. And you see, of course, there's some obvious thing. You restrict to V, and then you restrict to W. No, we did the other way around. Restrict to W after that. This is the same as restricting from So such a thing, and it's this is all automatic here in this case. So here in this case, this is automatic. This follows just immediately from our definition of a complex manifold. Now this thing that we have here, this association, is called a pre-sheaf. So, if you like, this function, it's an example of a pre-sheaf. Now you'll see in a minute why I want to save the word pre, keep this word pre. I will dump it in a minute, but let's leave it there. Let me do another example, which will make you, well, let me just note that if you have F alpha in O x u alpha, so you take a covering, open covering. This is all trivial, but I just sort of note these obvious facts. You have a bunch of F alphas with the property that F alpha, well, let's even do it in the language here, the restriction from U alpha to U alpha intersect beta of F alpha equals the restriction from U beta to U alpha beta of F beta. Right. So you have to draw a picture so you know what you're doing. This is U alpha and this is U beta. And if you have such a covering so that this is always true, right? Then there is a unique global function in Fx, or where, say, I don't, open cover, maybe even let's make it a V. So any open set here. Then there's a unique F here, so that the restriction of F from V to U alpha is equal to F alpha. Right? You can piece together, maybe you call this piecing together things. Yeah? That's completely obvious. Right? This is maybe a point number one. And a point number two that is completely obvious in this case is that if you have two functions on the stuff, and the restriction, so I have to write the map, the restriction from the big space to the covering is the same. I mean, these completely obvious axioms for all alpha and beta.
G.
But no, that's I just sorry, there I go again. Right. No, I finally got it right. So each restriction is the same. I mean, it's complete. It's the same for you all, for all alpha. Then, of course, this is really trivial. Yeah, but these are two axioms that are fulfilled in this example. And you may laugh, but now I'm going to take another example. Well, let's see here. What do I want to take? The Ramco homology, maybe. Homology. I want to think about whether I want a sheaf or a co-sheaf. So, if we take a differential form, what can we do? We can restrict differential forms, right? We can restrict differential forms. So, let's look at the mapping. U is mapped to the Duranko homology. I don't know, I just say it doesn't matter, some Duranko homology, I don't care, any, the whole thing of U. Okay? And certainly there's a restriction if a U contains V. Durand cohomology is closed forms modulo exact forms, so you can restrict differential forms, right? Okay? So there's a restriction map at the level of differential forms, which induces a map at the level, it maps the Durand cohomology, it restricts, okay? Now, watch. This is, everything's perfect. Now, let's look at axiom 2. Cover, I don't know, X with contractible open sets. U out. Okay? You do it all the time, right? When you contractible open sets. Okay? That says that the restriction from X of U alpha of the Durand cohomology map, this map, well, this is 0, and this map is the 0 map, always. So, locally speaking, any two cohomology classes satisfy this property because they all map to 0. They're trivial locally, right? It's just ridiculous. Globally, there may be highly non-trivially different. Maybe one is identically 0, and the other thing is a non-trivial cohomology class or something.
Can you explain what contractible is?
Contractible. Well, okay. I will say what it is, but let's just take it to be diffeomorphic to a ball, okay? And I believe that's essentially the definition of contractible. So what I mean by this is this, that if you have some base point, that this base point is a strong deformation retract. This is what I mean by contractible. If this is, say, U alpha, of U alpha. And what I mean by that is that you have a homotopy from the full ball, which ends up at a point. Okay? And that's pretty close to diffeomorphic to a ball. I'm not sure these things, I have to think, I'm not very good about this minute, but you might as well assume diffeomorphic to a ball. Anyway, if that's the case, as you well know, you have Poincare lemma, so every cohomology class vanishes. Right? So, okay. Okay, so this thing's always 0, so you may very well have two classes here, I don't know, class of omega and class of mu, two classes. Well, they may be completely different, but they both get mapped to 0. And that violates, I mean, axiom 2 is not, so that's typical when things go wrong. Okay? But of course, things that are function theoretically oriented, things like this will never go wrong. So that's that. So, definition, if you like. Pre-sheaf. So I didn't even define pre-sheaf, but I gave you an example of a pre-sheaf with the functions here. Right? It's a functor from the category of sets to, say, abelian groups, not necessarily abelian group to groups or something like this. Some algebraic structure. A pre-sheaf which satisfies axioms 1 and 2 is called a sheaf. Now that's sounds like a very funny definition because of the word sheaf. I mean, how does it happen? What is this word sheaf going on here? So I will explain, I will never use this explanation, but I will explain why it's called a sheaf. Okay? You see, the idea is to piece together local objects to, using like these axioms, of course, to obtain global objects. Now, the global object might be something on the full manifold X. So let me say global object in S of X. So S will now be the thing associated to the sheaf we're dealing with. And so you really want to understand, locally, so what are the global objects are completely clear. It's the stuff that's in S of X, the global holomorphic functions, for example. The local objects, the most absolutely local objects. Absolutely local is the germs at a point. So absolutely local at a point is and we often write this in test math cal at a point. And what that is, you have to tell me because I don't know this notation, but it's something like this is the inverse, I think it's the inverse limit. So with u containing x of S u. Now, is that the inverse of the direct?
What is the definition of inverse limit? I mean, which one goes which way?
I never know.
And what is the x here? Small x.
Oh, okay, yes. Because x is completely stupid. You caught me again. It's wonderful you people watch P. So, P is fixed, right? So I have to draw a picture of it. P is fixed. And you take some u, and here you have S of u, and then you have some v, and here you have S of v. And this inverse limit, it's a directed system because you have then stuff in here, and this is W, and then you have S of W, and so you can restrict to W here, restrict to W here, and then you go in inverse limit or direct? I think you.
Direct limit.
I think this is inverse limit, right? Yeah. So maybe we should write this. You go in this direction. Yeah, and you get something at a point, right?
I think it's direct limit, maybe.
Is that the direction?
Maybe I'm wrong. It's okay.
I think it's interesting.
Depends on which way you write the order.
What is S of u?
Huh?
What is S of u?
I just told you it's a sheaf. So S is the sheaf now. So it's a map from an open S of u. Remember, I didn't write it down. I just wrote it for homomorphic functions. But you can imagine when u goes to S of u. It's a mapping. It's an association. It's very abstract. But the first example is S of u, O of u is the holomorphic functions on u. M of u is the meromorphic functions on u. C infinity of u is the C infinity of functions on u. H1 Durham of u is the Durham cohomology of u. So then we become abstract. I think you're looking like a question, or not?
Yeah. How do you take limit of sets?
By the restriction, by inclusion.
Groups.
By inclusion.
What's the limit of the groups, like modding out by some equivalence?
Huh? What are you saying?
They're taking the inverse limit of the groups, or whatever the algebraic structures.
That's not his question. Because Well, it is, that's what it's called. But you need an ordered system. Or a partially ordered system. That's all I'm saying. You have a partially ordered system, then you have an inverse limit. Okay? The partially ordered system is given P is the set of open sets containing P. And is partially ordered by inclusion.
I think you don't know the definition of inverse limit for sets, right?
There's no definition here. I'm just taking that partially ordered system.
Right.
That's it. And then, yeah?
Though, I mean, the question is what are the objects in the, I mean,
The objects are some groups or something like this, whatever it is. You mean these objects here?
Inverse limit, yeah, I mean, what?
These objects here?
That's a set.
This object is, I didn't make it precise because I don't want to make it precise, but if you insist on making it precise, they are groups. So this is a functor from from the category of sets to the category of groups. Right? So the restriction morphisms are group morphisms in that case, right? But actually I don't want to be so precise because in fact, quite often these will be O modules. Right? I mean, I'm very interested in holomorphic functions and so on. I mean, there'll be some sort of modules, some sort of algebras. And I don't want to say abelian because quite often I will be dealing with non-abelian groups that arise, for example, in vector bundles. So I would prefer just to say some algebraic structure where I have one operation so that this whole thing makes sense. Okay? And then the way people draw this, here's P, and here is SP, and they say the germs of the sheaf at P. Okay? And then, in the neighborhood of P, here's an open set, for example, some small open set W. You have all sorts of germs. Nearby you have germs, nearby you have germs, nearby you have germs, nearby you have germs. You have the union of germs. Okay. So the sheaf space itself, S, is the union over all P in X of the germs. So at each point, I mean it's completely formal, don't try to get excited about it yet. It's just completely formal. At each point, you hook in there these germs. Okay?
So, Professor, can you please explain again how do you get the S of P? I still couldn't understand this limit.
It is defined as the quotient of a huge space modulo an equivalence relation. I'm now going to tell you the equivalence relation. Okay? So I take S in SU, let's say S1 in SU, in U1, and S2 in U2. Here's U1. Now, we're only allowing sets which contain P. Okay? So P's in here someplace. And here's U2. Okay? And I say, and now I'm looking at, if you don't mind, I'm looking at the direct, this is an unbelievable thing. I'm looking at the direct sum of all of these groups. I mean, it's an unbelievable, I don't even know if it exists really. I hope there's no logical problem here with this object existing. It's parameterized by the power set, no, the open set, so it's probably not too bad. So, of this direct sum, and here I'm going to have an equivalence relation. These things that contain P. And now I'm going to define the equivalence relation here. S1 is equivalent to S2 if and only if there exists a W. Of course, P should be in it, so that the restriction from U1, this gets on my nerves incredibly, U1 to W of S1 equals the restriction of U2 to W S2. It just says, locally at P they're the same. right? They're defined here, defined here. I don't care what happens outside of P. If you allow me to shrink arbitrarily much, then the two things are going to be equal. Is that sort of a reasonable way to feel about it?
Is it the same as you just take all the intersection of S of U, which U contains P?
You take all the intersection, so what? You get a point, maybe. So, yeah, that means you might watch out because you might think that then the value is the same there, not the whole germ. What?
So if, for example, if we work with X being a one-dimensional complex manifold, yeah, all the functions look locally as polynomials of
Let's
X
do homology.
squared, look whole,
Power series set.
they look like X squared, so you get a germ as being X squared.
That's exactly right. So let's look at that. So, by the way, you're coming close, say, to the Weierstrass. This thing really was in Weierstrass's head very early in this business. You see, let's take Mihai's example, okay? So, I mean, you don't have to be fancy about it. Just take the unit disk. Okay, so X is the unit disk. The unit disk in one variable. And P is 0. Okay? And now, if you have a function which is holomorphic on U, and U contains P, then F has a power series expansion, A nu, Z nu, in the neighborhood of P, in the neighborhood of 0. Right? Right? So what you're going to do now, you're going to look at that germ-wise. You're going to restrict and you're going to restrict and restrict. So what you're going to do, you're going to find this function here as a germ as its power series, which converges somewhere. You don't care where it converges. The only thing you care is, I mean, because you're allowed to take it smaller and smaller and smaller. You don't care, right? You don't care that it converges. It converges somewhere. If you take some representative, it'll converge somewhere. Okay. So, okay. This is, okay. And now, look what you have. I'm going to put this in the middle here more. You have an element here, and it's a convergent power series somewhere. And you're taking a representative of it. That means you get something here. Right? Because it's converging somewhere and you can look at its germ in each place. Right? Now you take another function.
I mean, that's a good case. Can it happen that it has radius of convergence 0?
I'm just not hearing it.
Can it happen that it has radius of convergence 0?
There's no, because no. That's somewhat what Sentau was wanting to do. He's wanting to just take the whole intersection, and then somehow you would get a formal power series ring, I think. Here we're really getting the convergent power series, but with no guarantee of how big the radius of convergence is. Okay? So you take another one, and this is a bad picture, but this is another one like this, and another one like that, and so on. And you see the sections of this. Now we go to farming. Farming in countries where they have wheat. India doesn't have wheat. I don't know whether it has wheat or not. It has a lot of wheat. So you know, in the fall, late summer, they cut the wheat or cut the grass, but particularly wheat. They put it this like this, and they bundle it like this. In any mountain place, you see it also. Yes, and that's what this thing is. This is a sheaf space. Okay, and the thing above a point is called the stalk, and the whole thing up above is called the sheaf space. And these things are called sections in the sheaves. Yeah?
I don't want to interrupt you.
No, it's okay, please.
But can you please give an example of something that is equivalent to F? In that case, you have a power series locally. What is equivalent to F? Like, is there anything equivalent to F except for F? Like all the functions have different power series.
Well,
Here you're considering the function and the domain. So if you consider, I mean, if you have a small
That's
domain,
right. That's
and a
right.
function,
so we're carrying with it. I think that I'm very happy you said that. You're carrying two pieces of information. You're carrying I mean, in some sense, you're absolutely right, because, but you have the function on this thing, it is f, and the function on this thing is f. But really, it's the function with the domain. Okay? And now I want to tell you how Weierstrass thought about this thing, and then you'll start to get a little bit excited. Let's take, so, okay, before I tell you about this, the topology, if you want to take a topology on the space, the open sets are these things. So the topology is horizontal here. It's an unbelievable topology, but that's the way it is. My teacher, Andreotti, because he's Italian, he calls it spazio lasagnato. So it's very beautiful. So you see the topology is like that, and really the open sets give you sections. Lentamente.
I think one kind of particular, I mean here these restriction maps are also injective, which is
Yes.
particular.
So that's a very particular thing, the identity principle.
I guess that's why it looks a little bit funny. I mean that these local SPs are. I mean you cannot easily find something which is equivalent, but not.
That's right. Let me though, there's a very interesting, from Weierstrass' point of view, and the point of view of 19th century complex analysis, which is very strong. Of course, they never wrote this picture, but if you don't mind, I'm going to draw you an amusing picture. Let us consider C minus the origin. Okay? And let us consider, then we have some, maybe I put here's where the origin was. It's very hard to see here. So then we have all of these stalks of holomorphic functions here, with a hole here. Right? Now, we were talking at lunch, I mean, about the proof of the Riemann mapping theorem and so on. Somebody tells you should define this function square root of z. Right? On the function. Now, this function is not defined. In 19th century mathematics, this function is completely defined. They did not worry about this in the slightest. And the reason Weierstrass did not worry about it is, you know what you do, here's C. Oh, it should be the disk. Let's make it the disk. Here's the disk. So what you do in a modern version of this subject, let's make something here. You say here, okay, there's some problem here, and this is e to the 1/2 log z, and then you write down the power series of log z, and you do all sorts of fiddling around, and you get some representative of it here, right, with some choice, right, plus or minus, it's called a choice. Maybe you don't know what plus means and minus. So that means you start here, and you have some section, right? Well, this is the punctured disk. And then Weierstrass, of course, he said, okay, well, I don't care. I'm just taking where this function is defined. These people are really abstract. They're much more abstract than we are. This function, you call it a power series. It's your point, exactly. You call it a power series here. It's not a power series. It's defined someplace. And he follows it. So you see, an open set in the sheaf space is really the function, right? It's a multi-valued function, perhaps. Okay, so at one point, this may be some sort of triviality, but globally it's not a triviality at all. If you look at in the sheaf space where all these, do you understand where I'm going? You continue the power series and continue it, and you come around with a different value, which happens to be minus the other value. It's not like log. Well, if log, you'd have infinitely many of these things. These things really are in the sheaf space. Okay? They're not sections of, they're not well defined globally in the pre-sheaf, but they're in the sheaf space. And this is one reason to do it. Okay? Mihai, does that help a little bit? Maybe? It's what he said. What's your first value?
No, I got what Professor Kevin said.
How do you shorten that? Saba, but that's a fish in Japanese. So,
Maybe Sabia?
Yeah, people call me Sabia.
Sabia. Oh, that's nice. Sabia. What do you say, Mia?
For one.
You said something here, or not?
Yeah, I understand what Professor Kavan said with the identity principle and why you cannot identify something. You cannot you cannot write two equivalent elements because of the identity principle.
That's right. Okay, so we're on this now. So again, the definition of sheaf is a function from sets into, say, group, which is compatible, the mappings, the morphisms, the groups are compatible with restriction. That's the functor that you're talking about. That's a pre-sheaf, and if these axioms are fulfilled, it's a sheaf. And anything dealing, which is a function theoretic thing, is obviously going to satisfy these axioms. Okay? Good. Now, the next step.
Is this the design of your shirt or is it something that you dropped on your shirt?
What? What is from?
No, no.
Did you drop some ink on your shirt or is this
No.
a design?
No, it's just design. It's strange.
Okay, now I will give you another definition of a complex manifold. Okay. So a complex manifold, this is not necessary because we all know it, but I mean, let's just take a definition here. Is a pair X, OX. Where you have some minimal restriction on X, maybe less as Hausdorff and pair compact and all this. I never know how these topological restrictions must be made, but I certainly have this in mind. Okay. And OX is a sheaf. OX is a sheaf, but the statement is for every P in X, there is an open neighborhood Who to P. This is I'm very sloppy in my English, I'm sorry. U of P. And a domain in Cn a domain, say, B in Cn such that this sheaf is isomorphic to such that O, B, U, this sheaf is isomorphic to this, I'm sorry, where the heck am I? OXU is isomorphic to OCN. Okay? It's the same definition. You worry, first of all, it says locally, the holomorphic functions are like holomorphic functions on Cn.
Professor, which structure does this isomorphism preserve? I don't know what is the...
This is an isomorphism of sheaves.
Yeah, but what kind of structure then?
Well, you're worried about whether it's an isomorph. Okay, this is an isomorphism of, I don't know what the minimal, it's a very fine question. I would say it's an isomorphism of C algebras. Is that what your question means? I don't know, you see what, it's more than, I think it is, we need more than an isomorphism of groups, for sure. The multiple, right? Yeah. Okay, it's a very good question. That, I think
Isomorphism of algebra, is it?
yeah, I mean, you have multiplication, addition here, and the vector space structure, of course. Maybe just an isomorphism of rings. You see what I'm saying? This may be a delicate question. And you know, I'm a little bit sloppy on this, so I apologize. So, but it's a bit, okay, so it's, yeah. It means, this is really, this takes this sheaf, this takes this complete functor here over to this functor here, which we all know. Okay? And you see, since restriction mappings are built into this definition, right? And since these things are sheaves, this gives us the old definition of complex manifold.
So the restriction maps are, I mean, is there any assumption about what sort of maps the...
You mean the algebraic nature of these maps? Sure, I mean, whatever algebras you have, it's a morphism in that category. Okay? So this is, these are restrictions are isomorph, or algebra morphism. Yeah?
In the first example that you gave,
Hmm?
in the first example that you gave, if you do the procedure with the germs and you put them above in a vector bundle, if you restrict to an open set U, do you get above in the bundle? Do you get O of U? I mean, you do the
No, you get the sections. You will get O of U. Yes. That's a very. I understand what you're saying. So let's try to make precise what you're saying. You start with a pre-sheaf. You take this germification. You get all these things. Then you go backwards again. You take U and you ask yourself if you get O of U. And the answer is, if you equip the topology with the topology I said, that locally open sets are little pieces like I just said, then of course you're going to have unions of open sets, and the answer is yes. And let me just say what the theorem is. A pre-sheaf is a sheaf if and only if it works. You go down and you go back and you get the same thing. That's the reason, that's really the reason.
It's practically a definition.
That's the reason, everything's tied in, it's exactly the definition. You don't need the topology really, I'm going to avoid it. It's really this fact, you don't get anything new by going back and forth. So if these axioms are satisfied, it's great, just forget it. But I just want to tell you, if you talk to your friends and that learn about sheaves there in algebraic geometry, at least you should know about the spazio lasagnato space and all of this stuff. But it's really axiom 1 and axiom 2. And that means if you go in and back, you get the same stuff. Okay? And this is extremely convenient, right? That all you need is what we call a ring space. So the word ring here is used, so maybe we only need ring structure here. And this is a language of Grothendieck, I think. And that's it. Well, now a complex space. Okay. So you see, well, I'm saying here we're singularities now. Okay. So you see here we need some local model. This you should think is the local model. Okay. So what is the local model for a complex space? So the local model is an analytic subset. I'm going to have to add something to this. Analytic subset of a domain. Cn. That's if you're in sort of primitive mathematics. you are in, well, let's a little bit more sophisticated mathematics. You have a domain D, and you have F1 through Fk, finitely many, everything's Noetherian here, so you're going to always, with Hilbert basis theorem, really think that everything's finitely generated. Don't worry about it. You're really looking at something like a bunch of functions equal to 0. And so that's your idea about an analytic subset here. So this analytic subset is in here some set. Oh, this morning I called this, let's call this A. I'm not finished with the definition, so this is A. And this analytic subset, some funny singular subset is in here. And that should be the local model. So let's try it. So a complex space is a Hausdorff space, paracompact, blah, blah, blah. And a ring, right, which is locally, in the above sense, isomorphic. And now I hope you're going to get mad at me. Isomorphic to A, OA. Okay? So the locally isomorphic to this analytic set. And now you're going to ask me a question. What's OA? Okay? Right? What's the right?
So what's D in all this business?
So D is some open subset in C, in some Cn, it doesn't matter what. And in some sense, you will see at the end it doesn't matter where it is. It's just some place where you can define the analytic subset as a zero set of a bunch of functions. Okay? You don't care. Actually, you will not care about D at the end too much. Okay. There's no canonical place where anything lives, right? It could be there, there. Right? Okay. You're going to ask me what is OA, right? And so to discuss OA, there's a sophisticated problem that starts happening, but if you define it with a bunch of finitely many functions, and those functions are important to you, then you should look at the subsheaf of OD, which is the sheaf of ideals generated. So this is at the sheaf level of ideals generated by these functions. Okay? This means generated as an ideal sheaf here. You must. This is of course a ring. These stalks are all rings, so it's completely clear what it means an ideal subsheaf is here. And so you have an embedding here. This is morphic. You can see what this all means. And you just take the ideal generated by these functions. Okay? And then, of course, one definition of OA is just that. The quotient sheaf, because it's locally, holomorphic functions on D, modulo those that vanish on A. I mean, this is some trivial definition. Right? Now, this is a sophisticated definition because it is very possible that the radical of I is not equal to I is possible. You know that, of course. So, yeah? So what's going to happen here, for example, if A is the origin in C, right, maybe the function you've taken is Z squared, right? So you would be looking at the power series in Z modulo the power series in Z squared. So as you see, it's not just the constant function. It's constant function plus first order phenomena, right? Right? This is, you get Z in there. It's not equivalent to 0. The power, just Z is not equivalent to 0. So this is possible. And for a first taste of complex spaces, you should assume, though, that the space is reduced, which means I is the radical which means that that f equals 0 if and only if all values of f equals 0, all a and a. You see, that's the problem in these things. The function z squared, the value of z squared is 0, but z squared is not, z, right, in this power, in the quotient model. The value of z is 0, but it's not the 0 function. Okay? So that is not a reduced thing. And these things really, really occur in complex analysis, algebraic geometry. You can't avoid it, but at first, for sure, you should take reduced space.
Can't you just request like that the ideal is the whole ring?
That's right. I know what you're saying, you didn't say it quite right. You request that the ideal is the sheaf of germs of holomorphic functions that vanish on A. That's what you're saying, right? Take all. And that's the same thing as going to the radical. Okay? But that's, I prefer your formulation. And so that's what we will do. Okay? So you just take the obvious sheaf, that's that, just locally isomorphous to that. Okay? So now algebraic geometry is very easy. Because you just have to tell me what the open sets are, because locally, you need to know what local means. And you want to know what local means. And then you have to tell me on those local sets, what are the algebraic functions? Well, if you think for a little bit, you will see what you will come up with immediately. Okay. The local sets are where algebraic functions converge, are regular. But algebraic functions are rational functions. So where they are regular is a huge set where the denominator is no longer 0. These huge sets are called Zariski open sets. Okay. Then you have just the sheaf. You have the sheaf of regular algebraic functions on such things. Well, it's the same. It's just that you're working in the Zariski topology and not in the Euclidean topology. Okay. Well, let me just, I think that's a good place to stop today. I'm a little bit, I want to catch a train, and to get this is pretty formal, right? Okay. And next time I will really use this machine, because you see, you have, it's a really good algebraic machine to use. I think we all use it nowadays. It's nothing fancy. Okay. You look like you might have a question, Sita.
No, I just don't, I have questions, but I just don't know how to ask.
Yeah, I know that feeling. It's a terrible feeling. It's a funny feeling. So think about it, maybe send me a mail or something on the weekend, I'll look at it. It's
I just feel it's a bit impossible that this manifold is isomorphic to the A.
locally. It's not a manifold. It will have singular.
I mean, the XOX is the manifold.
Yeah, X, yeah, in the first case, yeah.
And then what is D here? D is some,
It's a domain in some CN.
so arbitrary domain is.
But why do you impose this restriction? Like, why don't you say the function is globally defined on Cn, and you take the zero set to be in Cn? Why do you need a domain, like a special domain?
Yeah.
Any domain, it's nothing special, it's any. Given a point and an open neighborhood, there is a domain.
Yeah, but why do you introduce the domain into the discussion? Why don't you say just in Cn? Like,
Yeah, because
you
the
say-
thing might not be global. It might be, a global analytic set in CN is really some very special guy. I mean, give me a break. I take, you know, one complex variable. Take a sequence of points in the unit disk, you know, as an example, that are everywhere dense on the boundary. You easily construct such a sequence, and you can do all sorts of interesting function theory with those points. You all right? I mean, take a holomorphic function which vanishes along those sequences. That's a lot different than a holomorphic function that on C someplace.
Okay.
We really want the possibility of all sorts of local phenomena.
So you want to define functions like the square root and stuff like that?
Yeah, that's another reason. That's another reason, exactly. I don't worry, I want a square root.
Hmm.
I have two definitions, what do I care? Okay, both will be there. That's a very interesting point. I localize, and both definitions will be there. And there's no discussion of plus and minus.
The point is, X is locally like a piece of an analytic set, not the entire analytic set. Only like a piece.
Well, X is local in analytic set.
Yeah, that's
Right?
But the F's are just defined on these.
That's the point.
They're
That's
defined
the
on
point. The
these.
set itself somehow pieces together.
Yeah.
But the F's, maybe you may have no global F's.
Yeah.
Of course, it may be compact.
Mhm.
In fact, our example is going to be, yeah. But you have all sorts of local stuff, and you really need to understand what the local stuff is. And it's just in this sheet space, in this ring space. That's it. It's a good language.
And by domain, you request from it to be connected.
Actually, I was a little sloppy there, probably not even, so. Okay. Okay, thanks, I'm gonna take off. See you on